Okay, what is the trajectory? Trajectory, also called pathline. A trajectory is the path, the spatial path, followed in time by a given particle. So, if I have a particle that at reference configuration is there, at different times the particle is moving. Okay? And the locus, all the positions occupied, the spatial positions occupied by this blue particle along time is what we call the trajectory or the path line of the particle. Of course, different particles, the green particle that at the reference configuration was here, then follows a different trajectory, and the red particle a different one, and so on. Okay? How do we obtain the equation, the mathematical equation of the trajectory? Well, it's a trivial issue if you know the equations of motion. What are the equations of motion? The equations of motions provide what is the spatial position along time of all the particles identified by the label of the particle, by the material coordinates, and time. If I just specify a specific particle here, for instance, x equal capital star x, then I obtain three functions of time, which are the three components of that line which we call trajectory. So a trajectory, the equation of a trajectory, can be obtained from the equations of motion just by specifying the arguments of the material coordinate, by saying material coordinates is 1, 2, 3, so I am identifying the particle 1, 2, 3, and then this equation becomes a function of time. Three functions, because this is a vector equation. There are three equations. These three equations are the parametric equations of the trajectory. Okay? So that's a trivial issue. Look, I could also obtain the equation in a quite more geometrical, differential geometry way, which is, we said that the velocities are the material derivative of the equations of motion. So if I differentiate these equations of motion, the spatial equations of motion, with respect to time, I obtain the velocities. So imagine that I know the velocities, and I want to obtain the trajectories. It is the equation of motion. So this is a system of equations, three ordinary differential equations. Look that we involved here differentiation with respect to time. So here there are three because this is a vector, three component by component, ordinary differential equations, where the unknowns are x, y, and z, or x1, x2, x2, x3. And then, look, you are supposed to know how to integrate a differential equation. We'll see examples. And the examples that you will do would be so easy that you won't have difficulties to do it. Okay? But the concept is that by integration, that set of ordinary differential equations, three ordinary differential equations that establish that derivative of the path lines or the trajectories with respect to time have, by definition, have to return the velocity, which is a function of the path lines x, small line, and t. That is a set of partial differential equations, first order. Probably you should know also that the integration of three first order ordinary differential equations is determined accepting three constants. So in the process you will realize that. Just the process of integration returns a certain function of t, but also depending on three coordinates. So what are these three coordinates? For every three constants. For every value that we provide to this is what is called a family of curves. And this C1, C2, C3 is just what? The label of the particle. So this is the non-canonical form of the equations of motion. So in other words, By solving this set of ordinary first-order differential equations, we obtain the non-canonical form of the equations of motion, where C1, C2, C3 are the integration constants, the constants that appear during the integrations. We'll see that in just a moment. And then we know that, as we have seen just a moment ago, if we have the non-canonical form, we obtain the canonical form. How? Specifying pot equals 0, placing capital X at the left-hand side, solving every constant in terms of capital X, and replacing here, and then obtaining the canonical equations of motion. So a way of obtaining the equations of motions from the spatial description of velocities is just integrating these equations here. We'll see examples of that. For instance, the example we have seen before. The example of this body moving along the circularly in uniform velocity had a velocity that was that. By the way, this was a stationary velocity, but this doesn't apply. Okay. So let's integrate that velocity. So let's consider the equations we have seen before, the equations of the trajectories. Derivative of x with respect to t is equal to b of x of t. So splitting the two equations that we have, derivative of x, derivative of y, equal bx, by, bx being the component x is omega y, the component y is minus omega x. That's what we have here. So, this is a system of two differential equations, two first-order differential equations, because we differentiate with respect to t, and we have to solve that. Okay, well, ways to do that. Don't worry too much about that. You maybe have been explained. Have you taken any course on differential equations? Someday, sometime in your life, probably. But look, the way that we do that, imagine that I take the derivative of this equation. So I obtain the second derivative of that equal minus omega times the first derivative of that. But the first derivative of that is that one. So I just can differentiate that with respect to x is minus omega. So finally, by differentiating the second equation once again, second differentiation, I obtain a second order. That is second order because there are second derivatives of that equation. And this equation that has a very known solution, you can look for it at MATLAB or whatever that you want, or any symbolic program, and the solution of this equation is that x equals c1 sinus of omega t minus c2 cosinus of omega t, y equals c1 cosinus of omega t plus c2 sinus of omega t. So this is the integration of the equations, right? Look, that same constant of integration appears. So this constant of integration identify one of these curves. What is one path line? What is the motion of one given particle? How is the particle identified? By the value of these constants. Are these the canonical equations of motions? No. Why? Because C1 and C2 are not the position of the particles at that time, reference time. How do we obtain the canonical equations? Well, these are the equations of motion we have identified. Now we set t equals 0, and we add that these equations, when t is equals 0, return here capital X, capital Y. That's what we do here. And we see the x is equal to C2, and y is equal to C1. So now, replacing C1 by y and C2 by x, I obtain the equations of motion now in canonical form. So far, so good. Okay? Another equation, a streamline. What are the streamline? Maybe you have also heard this notion in your fluid mechanics or hydraulics course. Is in Spanish is línea de corriente, línea de corriente. Okay? What is the streamline? Well, the definition of this line is rather geometrical. You know, imagine that we know the velocity at a given time, the velocity field in a spatial description. So I know what is the velocity at every point of space at time t0, okay? And I know at time t1 the velocity at every point of space, which is different. The vectors describing the velocity are different. Okay? So, at every of those times, I could construct what is called the envelope. What is the envelope of a vector field? For instance, this vector field has an envelope which is a family of curves again. A family of curves that have the property that they are tangent to the vector field at every point. So given a vector field, what is called the envelope, envolvente, embolicant, of the vector field is a line, as a family of lines which have the property that at every point of the space they are tangent to the vector field, or the vector field is tangent to these lines. That's what's called the envelope. So sometimes if we had been given this vector field, probably if I requested you to plot what are the envelopes of this vector field, you probably would have plotted these lines here, okay? And in that case, you would have plotted these lines here, okay? So there is, at every time, there is a different family of curves which are the envelope of the velocity field at this time. These are called the streamlines. So look, the concept is that in general, the streamlines change at every time. At this time, the streamlines are those, and at these times, the streamlines are those. Why? Because the vector field changes in time. By the way, could you tell me one case in which the streamlines wouldn't depend on time? Could you please think of this? Look, what if that vector field is stationary? If it's stationary, then that means that it doesn't change with time, the spatial description of this vector field. So that would be that at time t0 would be that, and at time t1 would be the same, and at time t2 would be the same, and a long time would be the same, if the vector field is stationary. So in that times, the envelopes wouldn't change a long time. And that is what we call, then in that case, the streamlines are constant a long time. Okay? Mathematically, how do we obtain the vector field? Well, it can be proven that something that precisely looking at the velocities and the tangent vector to the streamline, which is a vector which has the components dx, dy, dz, and the velocity having the components bx, by, bz, have to be parallel. That's since they are tangent, the tangent vector and the velocity are parallel vectors. So if they are parallel vector, the components are proportional. All the components are proportional with the same constant of proportionality. If we call this constant of proportionality differential of lambda, that equation, these three equations, that in fact are three equations, can be written in that way. Differential of x divided by d lambda equal differential of y divided by b lambda, d lambda, equal differential of z divided by d lambda is r equals to b, the velocity. This is, again, an ordinary first order differential equation that can be written like that. Find what are the expression of x in terms of lambda, x being one of these streamlines parameterized in terms of lambda, such that the tangent vector, which is the differential of x with respect to lambda, is equal to the velocity. And look, the time appears here too. In general, time appears here, but time appears as a parameter. Look that here, we differentiate with this lambda, which is the parameter describing every of these streamlines. But we don't differentiate here with respect to time. Time is a parameter that says at every time we have a different velocity, so we'll have a different solution. Again, the solution of these first order differential equations is a set of curves, a family of curves, that will depend on three constants too. C'1, C'2, C'3. Okay? Then they will depend on lambda. And they will depend on t because there is one family at every time t. Okay, so this is a family of curves in which every family, every element of the family, every curve of the family is identified by giving values to the constants. Then this identifies one family, one curve. Lambda identifies points of the curves, as we had there. Lambda played the role of the time plate in the trajectories. And t here is a parameter that says at every time we have different families. Okay? So we see that also in an example. Okay, so we have seen two concepts now. The concept of pathline or trajectory and the concept of a streamline or envelopes of the velocities fields. Okay, so there is one theorem that is important that, look, in a stationary fields, in stationary cases, the trajectories and the streamlines coincide with each other. In general, look at the mathematics. Okay, in general, we have the trajectories which are given by the solution of this differential equation. dx, depending on t with respect to t, is equal to the velocity, which depends on x, which in turn depends on t, times t. And integration that provides the equation, a family of equations, which are the trajectories. Okay? Now, in the case of streamlines, dx lambda, the differential of the x with respect to lambda, the x of lambda with respect to lambda, equal b, which is a function of x, which depends on lambda, and t star t is the parameter, the time in which we are computing the envelopes. So, if time appears here, then these two partial differential equations are different. Because here we differentiate with respect to time, and time is here, and here we differentiate with respect to lambda, and lambda is here, different of time. But what happens when the problem is stationary? When the problem is stationary, you know that the definition of stationary is when the spatial description of the velocity doesn't depend on time. So this time here just drops, there is not here. And this time here, there is not here. So now look at these equations, just dropping the second time. So, to finish, consider that motion here, okay? That is the velocity, which is given in initial form in terms of space at time. This is what? The spatial or the material description of the velocity? What do you think? Pardon me? I have heard something. What is the x? The spatial x? The small x or large or capital X? Small x. So is the spatial coordinates. So velocity of every point is given in terms of the spatial points in time. That is the spatial description of velocity. Okay? And of course, we have three equations for the component 1, for the component 2, and for the component 3. Okay, let's now obtain the trajectories. Okay? We have to obtain the trajectory. So we have to solve this equation. Differential of x with respect to t equal the velocity. So differential of xi with respect to t equal the component I of the velocity, which is this one. Okay? So that is the differential equation. We have three differential equations here. We can integrate, every differential equation is separated, so we can integrate one by one. And integrating that, we obtain that the equations that fulfill these equations is that one. xi equal certain constant cy that appears at the integration of the, looking for the primitive of this term here, it puts a constant, cy multiplied by 1 by t. This is the integration of these partial differential equations. In terms of three constants, for I equal 1, I have C1, for I equal 2, I have C2, for I equal 3, I have C3. So these are three differential equations, C as a family of equations, fixing freezing C1, C2, C3, I have three equations, x1, x2, x3 a long time. This is a family of curves, okay? Every of these curves is a trajectory of one curve. Okay, that is for the trajectories, equation of trajectories. Equations of streamlines. Now I have to take the partial differential equation. Okay, what is the partial differential equation? Look, I have to differentiate x, I1 to 3 with respect to lambda, and make it equal to the velocities x, y with respect to 1 of t. Look, let's compare this equation with respect to the 1. What is the difference here? I differentiate with respect to t. What is the issue here? I differentiate with respect to lambda. So t here is just a parameter. In the integration procedure, you don't have to take account of as if it was a constant. And by integrating that with respect to lambda, okay, then we obtain equation, which is that one, which is this. xi equals ci exponential of lambda divided by 1 plus t. So look, that equation depends on three constants. Three constants. Every one of these constants, when you identify the value at every one of these three constants, I obtain a member of the family. And then lambda is that parameter that tells me in what point of this specific streamline I am. And t is just a parameter. For every t, I have different expressions, different family curves. Look that this is very different of this. These are the path lines, and these are the streamlines. Okay? Well, something that maybe you are familiar with is the concept of a streamtube, tubo de corriente. Streamtube is just a tube whose surface is made of streamlines. So every of the lines that define this tube is made of streamlines. That's something that is used in hydraulics and so on, and it's good that you are aware of the definition.